ahead and get started. I think it's 7 o'clock and we're getting going. We got a lot to cover tonight. Welcome to the Alachua Astronomy Club monthly meeting. And as always, we simulcast this. We have a few folks on Zoom. Art, give me a thumbs up if you can hear me. Okay, good. Okay, tonight we'll have our normal announcements and whatnot, and then Terry Dickensheet will be telling us all about the Europa Clipper as a members corner. And then we'll do our refreshment break, which is 15 minutes long, and it's right outside the front door. No food or drinks back in the planetarium after that. And then we'll hear from Dr. Jamie Tayar from UF about the Landolt Artificial Star Mission. Okay, since our last meeting, we've picked up 4 new members. Kathy Boyce, are you here? Welcome. John Thomas. How about Randy Hine? Or Steve Wilhelm? Okay, have I missed any new members? Okay, do we have any visitors tonight? Never been here before. Okay, you're a visitor. You're more than a visitor. Okay, we have 187 members, so we're pretty healthy. We need to get rid of this. I can't see. Okay, so there was a star party at Rosemary Hill. Was that the one for the public? That was our own star party. So as you can see, there's a nice couple pictures of how dark it is there. It's just a wonderful place to have a star party. It looks like it was great that night. And then Chiefland, there was one on May 17th. Once again, we had a nice little turnout and the weather cooperated. Okay, the next star party at Chiefland is on July 19th. And if you've never been there, that's a picture that Orlando took out at Chiefland. And it came out beautifully. You can really see the Milky Way out there at Chiefland. And for our new members, these events are on the website. And then you'll get automatic emails reminding you, and that's where you can register for events. And June 9th, some of our members went over to UF and helped out with the UF IFAST 2-day enrichment activity for 4-H teenagers. And they're working on experiments with astronauts and will be flown on the ISS. So I think we had Warren and Karen, and let's see, there is Jerry S. maybe. Am I missing anybody? Oh, Matt, Orlando. Okay, so, and you can see that it had a lot of light pollution, so it was challenging. But you guys got the automated scopes to work fine, didn't you? Yeah, maybe. Okay.
Well, it was a good experience.
Okay. And then on June 14th, the ATM that Matt put together was Tom Field, who designed the software at RSPEC, Respect. And it's based, and I'll show you a picture. You use that in the bottom center there is a diffraction grating. And you use that with the camera and your telescope. And with his software, you can see the constituent components of the star you're looking at in terms of hydrogen, helium, and iron and whatnot. So it's really cool. And our club bought a copy of the software. And we're right now borrowing Richard's diffraction grating, but we'll probably buy our own for the club. And did you ever find out, Matt, what the story is on letting people share that software?
Yeah, I think I've worked around as far as using I've got a little mini PC that may be able to travel if there's interest.
Okay, but it's really cool to be able to do that. And just like the numerous telescopes that we have that members can check out, you can check out that too. Okay, this hasn't changed, but on July 15th, our next guest for the Journal Club is Dava Sobel, who wrote The Glass Universe. And it's a really good book. I listened to the audio version you could get at the library, Alachua County Library. And it's about all the ladies in astronomy who've done magnificent things over the years. And they were treated poorly early on, almost like, you know, the movie Hidden Figures. They were just called computers. And over time, they drew a lot of respect and did a lot of very fine work. So it's a great book to read. Okay, Matt went up to the Cherry Springs Star Party in Pennsylvania. He got back just a few days ago, and he was there with his nephew. And I bet, Matt, you told your nephew to stand real still for that picture, right?
Yes,
Okay,
Just to have to stand for minutes straight.
yeah.
Told them about it early in the day, it was quite the struggle.
Matt, what is, go back there. Is that a plane or a satellite?
It's a plane.
Okay,
Yeah, that's just 3 minutes taken with a cell phone.
that's cool.
Whoops. Going the wrong way. Okay, and there's the entrance to the park. And Matt's wearing that same shirt tonight. He had a really nice shirt there. And when Matt goes to a star party, he's well equipped. In the foreground, that's all your stuff, right? Yes, so those stars can't get him by him at all. He's gonna capture them. And tell me about that image, Matt.
That's just an unprocessed image of the M17, the Swan Nebula.
Okay,
A couple hours, so just preview the process.
okay. Pretty amazing. Beautiful country up there. It sounds like it was cloudy for a fair amount of time, but he said the weather was relatively cool. Boy, would that have felt good. Okay, as we speak, Rich Russin, who's a club member who now lives in Maryland, he always goes to the Grand Canyon Star Party, so he's there right now. He said there's over 70 telescopes, over 100 volunteers supporting, and it's really dark there. He's had folks come up there, it's a public star party, folks come up and say, geez, I guess we won't see anything tonight, it's cloudy. And he'd say, no, that's the Milky Way. A lot of folks have never seen the Milky Way. And there's one of the Rangers, not sure if that's the one that did a Zoom meeting with us a couple years ago. As you can see, they're doing some daytime observing of the sun. Now that's a serious rig there. Holy smokes. And it started to get dark, darker. Time to turn on the red lights. And there's what you see out there, just super dark. Okay, well, before he went there, he always stops at Lowell. He knows the folks out there. Look how rich, there's Martians behind you. And they have opened their new Astronomy Discovery Center. Rich said it's amazing. And there's a nice wall mural. And look who sponsored that. Mike Toomey. He's a club member who now lives in Albuquerque. And he sponsored that. So that's a really nice thing that Mike did. So as you can see that they've done a real top-notch job there with that new Astronomy Discovery Center. Okay, on Saturday, I went down to Orlando to see our club member Joe Haldeman receive the inaugural Arthur C. Clarke Memorial Award for inspiring and educating the public about humanity's journey to space. So that's a big deal. The NSS. The NSS, that's a serious organization, and the award there, it's appropriate. It's the other gentleman's holding it for him because it's so heavy, and it's a black monolith. Where have we seen that before? Okay, we now have a little video that Howard put together.
Okay, hold on a second, let me make sure the sound is on. Okay, I'm gonna mute the microphone. Okay, go ahead and press play.
Okay, that's you have the opportunity to go on that. You have the opportunity to go on that.
Club email list and want more information about this, you can see me during the break. And I can get your email, so I can send you an announcement, giving more information.
Yeah, we've had a number of club members go on these cruises and they have just a wonderful time and they even have the captain of the ship chase around to just get them in the right spot in the hole in the clouds so they won't miss the eclipse. So they do a good job with those. Okay, you probably saw in the news the newest images, the first images from the Vera Rubin telescope, and they are somewhat fantastic. As you know, that's the largest camera in the world. I can't remember how many thousands of megapixels it is, but it can scan the entire sky in just one night, and it's just incredible. So be sure to go out on the internet and look at images. They'll be pouring in. Okay, does anyone have any announcements? If not, I will turn it over to Terry, who will tell us all about the Europa Clipper.
So remember to repeat questions when people ask their questions. Okay, all you have to do is hit the right arrow and it should be good. Cool.
Right arrow?
Yeah.
Hey. All right, good evening, everybody. So this presentation is not so much about astronomy as it is about space exploration, which is just as exciting to me because we'll be talking about the search for extraterrestrial life within our solar system. If you didn't know, there's currently a pair of probes on their way to Jupiter as we speak. One is called the Jupiter Icy Moon Explorer, or JUICE, which was launched by the European Space Agency. And the other one is called the Europa Clipper, which was launched by NASA. This presentation is about the Europa Clipper, but if you've got questions about either probe, I'll be happy to try and answer after the briefing. All right. So let's go to some background. Europa, according to Greek mythology, was a princess, and she was very beautiful and caught the eye of Zeus, who decided to go visit Europa in the form of a white bull and carry her across the sea to an island where he changed into human form and made babies with her. Europa lends her name to the continent of Europe and to one of the Galilean moons of Jupiter, which we're going to be talking about. Getting a little off the subject, we were talking about Arthur C. Clarke, but let me have a show of hands. Who has seen the movie 2010 or read the book 2010 Odyssey 2? All right, a lot of you, about half. For those that haven't, it's a story about a joint Soviet-US mission to Jupiter, and on the way, they discover life on Europa. Oddly enough, a decade or so later, we sent a Galileo probe to Jupiter, and it noticed something weird about Europa, that there were plumes of water coming out of the surface. And it was very smooth surface, almost no craters. So the surface of Europa is very new. Evidence of a subsurface ocean, perhaps. Well, we sent another probe a decade or so later, Juno. In Roman mythology, that's the wife of Jupiter. And it visited Jupiter from 2016 to 2018. And they decided to extend the mission after that. And then they decided to extend the mission again after that to check out some of the Galilean moons. And it is still in orbit around Jupiter today. Yeah, it's supposed to crash into Jupiter later this year. So Juno gets to meet her husband. Most of what we know about Europa today is from the Juno probe. We've also learned some things about Europa from the James Webb Space Telescope, where it discovered some carbon dioxide on the surface of Europa. even the Hubble Space Telescope has looked at Europa and seen some of those plumes, those water geysers coming out of the surface of Europa. So it is possible. That's one of the more likely places, besides Earth in our solar system, that might harbor life. So it's time to send another probe. And there it is, weighing in at 13,000 pounds. The Europa Clipper is the largest planetary probe ever built by NASA. And in all its glory, we're going to talk about this Europa Clipper. It was launched last October, last year, out of Cape Canaveral in a Falcon Heavy rocket. It did a flyby of Mars just this past March to give it a little boost, and it's going to do a flyby of Earth next year to give it that slingshot out to Jupiter, which it should arrive about April 11th, 2030. So it's well on its way. It is an orbiter flyby, so it's going to orbit Jupiter and do 49 flybys of Europa. Close flybys, we're talking about as close as 16 miles to the surface of Europa. 16 miles is really close. For comparison, I drove about 3 times that distance just to get here tonight. The objective of Europa Clipper is determine if Europa has conditions suitable to support life. Well, that doesn't say look for life. It says conditions are suitable to support life. So what conditions do you need to support life? Well, there's 3 things. You need liquid water, you need energy, and you need the right chemistry. Well, liquid water, anywhere we see liquid water on Earth, we find life. And Europa has liquid water. From what we've observed, right, some of the observations, scientists are estimating there's about 10 to 20 miles thick of ice crust, underneath of which is a salty ocean, perhaps a global ocean, with as much water as twice as much as all the oceans here on Earth. So that's a lot of water. Energy. Well, on Earth, we get our life energy from the sun. We're in what's called the Goldilocks zone, just the right distance, not too hot, not too cold to support life and liquid water. Well, Europa is far outside the Goldilocks zone. Those surface temperatures averaging about 200 degrees negative Fahrenheit. But its energy doesn't come from the sun. It comes from Jupiter and the tidal friction that Jupiter causes on Europa. Europa is tidally locked like all the moons of Jupiter, but it doesn't travel in a circle, right? It's an ellipse. And so as it gets closer to Jupiter, it gets stretched more. And if it gets further away from Jupiter, it gets stressed less. And that tidal friction creates heat in the interior of Europa. So we've got energy, we've got liquid water. Chemistry, we need certain elements like carbon, oxygen, nitrogen, phosphorus, sulfur, to make the chemical compounds we need for life. And hopefully that's what Europa Clipper is going to find out. All right. Well, if we're looking for life on Europa, why are we orbiting Jupiter? Why not orbit Europa? Or better yet, land on Europa, drill a hole down through the ice, send down a camera and see what swims up the lens. Makes sense? Well, there's a problem. And it's called radiation. There are big radiation belts around Jupiter. We've got radiation belts around Earth too. You've heard of the Van Allen radiation belts. Charged particles trapped by Earth's magnetic field. Well, Jupiter's a lot bigger, and its magnetosphere is humongous. It's about 20,000 times stronger than Earth's magnetosphere. And so its radiation belts are much, much bigger and much, much stronger than those around Earth. And wouldn't you know, Europa's orbit is inside the radiation belt. So it would be hard for any life to evolve on the surface of Europa. It would be deadly for us to try and walk around on Europa. And it's not good for our probes either. So what do we do about that? You can see here a depiction of the Europa probe on a very eccentric orbit around Jupiter. And perhaps a 21, 22-day orbit. It would only spend 2 or 3 days within that radiation belt, okay, that hostile environment. So that limits the radiation. Also, NASA has put a lot of the sensitive electronic equipment of Europa Clipper inside an aluminum vault. It's actually a aluminum titanium alloy vault to help give some protection from that hostile radiation. The other thing that does, since Europa Clipper can collect data a lot faster than it can transmit it back to Earth, it does a quick flyby, collect a lot of data, and then when it's out at apogee or outside of the radiation zone, it can be transmitting all that data back to Earth. So that's why. Getting there, here's a representation of the Europa Clipper's orbit. The light blue circle is Europa's orbit, and the Clipper is coming in. As it approaches Jupiter, it's going to fire its rockets to slow down, and then it also is going to use Ganymede and Europa to slow it down some more and kind of adjust the orbit, so we get those close flybys. That's pretty impressive. I think it takes like a pinball wizard to figure out the orbital mechanics of this thing. But getting there is only half the battle, right? We've got to also study Europa. And on board Europa Clipper is 9 different sensors. We're going to go talk a little bit about each of the 9 sensors. Starting with ETHIMS, Europa Thermal Imaging or Emission Imaging System. That's a mouthful. It's basically looking for heat. What are the hot spots on Europa where there might be water close to the surface or recent activity, transfer of water from below the surface to the surface. Then we have MISE, Mapping Imaging Spectrometer for Europa. So it's doing a spectrograph. This is in near infrared to find out what kind of chemicals, what kind of elements are on the surface of Europa. Then we have the Europa Imaging System, ICE, which is actually 2 different cameras. You've got a wide angle camera. Both the cameras are about 8 megapixels, but the wide angle has a resolution of about 50 meters per pixel, which is higher resolution than anything we have so far on Europa. And then has a narrow angle camera that's about 0.5 meter per pixel. So we're getting some really good mapping of the surface of Europa. About 95% of the surface will be mapped by the imaging system. Then we have the Europa Ultraviolet Spectrograph, or UVS. So these first 4 are basically all cameras. You got the far infrared, near infrared, visual, and ultraviolet cameras. So we've got a lot of looks in different wavelengths on Europa. And that gives us some foundation for the rest of the instruments. Next is REASON, radar for Europa assessment and sounding ocean to near surface. REASON is actually 2 different radars. We've got a high frequency radar that gives exact distance to the surface of Europa. So we can see the peaks and valleys. There's not a lot of peaks and valleys, but you know, the rough or the smooth surface of Europa. And then we have the low frequency radar, which is will penetrate the ice crust and the water, bounce off the solid surface of Europa, so we can measure where the thick and the thin icy surface is. We can get a more exact measurement and how big the ocean is. And we have the magnetometer, ECM. And this is measuring Jupiter's magnetosphere and also Europa's magnetosphere. Believe it or not, Europa has a little magnetic bubble around it. We think it's an induced magnetic anomaly from Europa, or from Jupiter's magnetosphere is interacting with Europa. And to get an induced magnetosphere, you kind of need an electrical conductor, like a salty ocean. Then we have PIMS, Plasma Instrument for Magnetic Sounding. Europa is orbiting in basically a river of plasma, all those charged particles. And PIMS has got 4 sensors. They're called Faraday cups and pointing 4 different directions. And so it's going to pick up these charged particles and measure the charge, the direction, the speed that these particles are moving. And in conjunction with the ECM, it's going to tell us some cool things about the interior of Europa. All right, the interior structure. Okay, then we have mass spectrometer for planetary exploration. If these first 4 were the eyes of Europa Clipper, then mass specs is the nose of Europa Clipper. As it flies by that low pass, it's going to sniff out the elements and molecules in the very thin atmosphere of Europa, and hopefully it might get to pass through one of those what they call cryovolcanoes or geysers, that's pumping out some of that interior of Europa, and check out what constitutes the ocean of Europa. All right, finally we have the SUDA, for Surface Dust Analyzer. If mass specs is the nose, then SUDA is the taste buds. So Europa is getting constantly pounded by micrometeorites and kicking up little fine ice particles, and SUDA is going to check those out, do an analysis of what that stuff is made of. All right, so those are the 9 sensors. I'm hoping that I'm going to be around in another 5 years or so when it gets to study Europa and we get some results, find out, is there possibility of life in that salty ocean of our neighbor out in space? Are there any questions? Europa Clipper. Yes, in the back.
Can it use more than one of those sensors at the same time? or
Absolutely.
all of them at the same time?
All 9 are running simultaneously. That's why it's picking up so much data as it does the flyby, because they're all being operated simultaneously. And then we can transmit all that data back to Earth. Yes. Yeah, well, it was launched last year and it's going to get there in 2030. So it's about 5.5 years. Yes.
What is the relative size of Europa compared to the Earth?
It's about the size of our moon. It's slightly smaller than our moon. It's a pretty large moon of Jupiter. It's one of the 4 Galilean moons. It's not as big as Ganymede, not as small as Io. Any other questions? Yes.
Was there backup? Any backup for the ones that you listed there?
Oh, backup, like, is there another probe? Well, there's JUICE. Okay, and European Space Agency has been coordinating with NASA as well. JUICE will be up there about the same time. It was launched in April of 2023, so about a year and a half before Europa Clipper. But it's on a slower trajectory, so it won't get to Jupiter until like a year after Europa Clipper. But they'll be up there together and they'll be able to compare notes. JUICE has a kind of a broader mission. It's going to do a couple flybys of Europa, but also Callisto and Ganymede. It's going to take particular attention to Ganymede. It's going to actually orbit Ganymede before it crashes. Both of them are going to crash into Ganymede. It's at the end of their mission, so one of them gets to watch the other one, I guess. Third one goes first. Other questions? Yes.
Are the sensors on Europa Clipper turned off until a certain point?
Yes, but it has been turned on and off. When it did a flyby of Mars, it tested out some of the sensors. So they can turn them on and off. Any other questions?
Okay,
thank you.
very well done, Terry. We have a small, don't go anywhere, come here. We have a small token of our appreciation for your Members Corner presentation. It's a commemorative Galileo 2 euro uncirculated coin. Cool, enjoy. Thank you. Okay, like I said, let's take 15 minutes for the refreshment break right outside the front door. No goodies back inside here. Take time to say hi to Dr. Tayar and our new member, and we'll see you back here in 15 minutes.
Okay, you're unmuted and your microphone is live.
Let's test 1, 2, 3. Okay, I think we have most folks back.
No, no.
You didn't set the bar very low. I gotta really jump now.
Okay, I'd like to introduce Dr. Jamie Tayar, who graduated from Caltech in 2012 with a BSc in astronomy, then earned her astronomy master's in 2014 and PhD in 2018, both at the Ohio State University. She was then a Hubble postdoc fellow at the Institute for Astronomy at the University of Hawaii, Manoa, before becoming an assistant professor at UF in 2022. She's interested in stars, how they grow, how they change, and what it tells us about the physics going on inside them. She works both on the theory of stars, thinking about how to make better models of their structure and evolution, as well as on observations using large data sets of photometry from the ground in space, as well as high-res spectroscopy to precisely and accurately characterize these stars. She also uses asteroseismology, the study of stellar oscillations, to tell us about the internal structure of stars. And as I understand it, among your students are Corin Marasco, is that right? And Mir Soshit.
Yep.
We know them because Corin was one of our guest speakers and we gave a scholarship to Mir. So
Yeah.
please welcome Dr. Tayar.
Great. Cool. Can everybody hear me? Excellent. All right. Slides.
Okay. So, where's it? So you incorporated hers into.
Yes,
Okay.
roll.
Okay, so I just hit the right arrow and you should be fine. And sorry, your
Sounds good. All
box
right.
extension.
So thank you all so much for having me here. And I was asked particularly to talk about this new mission called Landolt, which we're working on launching now. So thank you for the introduction. So I'm Jamie Tayar. I'm an assistant professor in the Department of Astronomy, and I'm really interested in stars, stellar physics, stellar evolution, trying to understand the interior, the time scales, what's happening on the inside, what we see on the outside, all about the rotation of stars and the mixing of stars and how they bubble and boil. And I use a variety of different techniques to do that. I make models of stars in a computer, trying to understand, what's happening on their inside and how it's going to affect what we see on the outside. I look at how stars vary over time and try to use that to understand something about what's happening in them. And then I also try and characterize stars. What are they made of? How hot are they? How bright are they? What is their size, their radius? What is their mass? How massive are they? And then I do a lot of work between comparing the models and the data, because it's very fun when you say, I have a prediction somebody made on the internet that says the star should look like this. And I have some data that says the star looks like that. And so then you know there's something physical that we don't understand by comparing the two together. And the Landolt mission is a stellar characterization mission for me. There are other components of it, but what I'm most interested in is using it to characterize stars. And so when I'm thinking about a star, I want to know absolutely everything about it, including really hard things like how old is that star? You look at a star and there's no obvious way to tell how old it is, but sometimes there are things you can use that correlate with the age. And to do that, you might need, the mass of the star or the radius of the star. What's the size of the star? But to figure out what the size of the star is, you usually have to figure out how bright it is and what its temperature is. Is it a hot star? Is it a cool star? That will affect how much light is coming out. And so all of this is kind of built upon a pyramid of understanding how bright are the stars. And so you all have looked up at the sky and seen the stars, right? But you look at a star and you say, okay, how bright is that one? And your eye is probably pretty good at saying it's probably fainter than this one and brighter than this one. And so that's differential or relative photometry. Which one is brighter? Which one is fainter? How much brighter? How much fainter? But all of that, if this one is brighter, doesn't actually give you kind of a fundamental answer to your original question, which is how actually bright is this star? Because when you're trying to measure that, it's actually really hard. It's not like a laser where you have it in a lab where you can actually say, okay, this is the number of counts of photons I am getting on a particular time scale using this specific instrument that I've characterized extremely carefully. You have to know what is your fundamental calibration. Who decided where 0 was? And different people are going to measure different things. If you've looked in 2 different telescopes, you've probably seen the same object look different in 2 different telescopes. And, you know, when you measure how bright it is, you measure how bright it is. Is that a question?
Yeah, do you use significant figures at all? I don't see a level of uncertainty there.
Yes. So the Landolt mission is particularly a precision mission. It's one where we actually care what the error bar is. It's very easy to say this one's bright-ish, and that ish gets shoved under the rug a lot. And part of the Landolt mission is actually dragging up that table of where do you get an uncertainty on this? Where do you get an uncertainty on this? Where do you get an uncertainty on this? Whose number are you using for that? And actually like working through the table of adding all those errors together to figure out what the uncertainty is. Because right now, I think when you look at a star and say, how bright is it? That number is usually measured to about 2%, maybe 2.5%. Which when you think about it, like how bright is that is something like seems very fundamental, seems very important. Like where's my 1% measurement? Where's my 0.1% measurement? And every other error in astronomy is stacked on how bright are the stars. And so if you've got a fundamental floor of 2.5%, that screws up all of that fancy cosmology you want to do, all of those, you know, habitable exoplanets that you want to study, because there is a fundamental uncertainty that you've been ignoring. And so, you know, you measure different things. You know, if you measure how bright the star is, you measure how bright it is in some wavelength. Maybe it's how bright it is in the green wavelength, or how bright it is in your particular telescope's filter. But that's not the same thing as how bright intrinsically is the star. And of course, there's also stuff in the way, right? We have the atmosphere in the way. There's dust in space between you and the star. The star itself is complicated. If you have spots on the star, right? You've seen sunspots on the sun. Those are darker than the rest of the sun. So when you're thinking about how bright is the whole star, like it also probably has spots on it. So how bright in what wavelength, at what band, at what frequency, using what measurement. So this is actually like a very fundamental problem to most of astronomy. And so that's what the NASA Landolt mission is designed to address. So this is led by Peter Plotkin, who's at George Mason University. And it's named after Arlo Landolt, who was an astronomer who for years worked on this very fundamental problem of which stars should we use as standards and how bright are they? And so I'm going to talk a little bit about the mission itself. I'm going to talk a little bit about the science of the mission. And I'm going to talk a little bit about kind of the long-term plan for the mission. I'm going to give you the caveat in advance that I'm working on the science of the mission. So if you have a detailed engineering question about lasers, I may not be able to answer it, but I will try. Okay, so this is a large team. So this is for NASA, this is the smallest class of mission that NASA does, called the Pioneers class. It's about a $20 million mission, which sounds like a lot of money until you have to actually launch something in space, and then it's not a lot of money at all. It is one where the lead investigator, the principal investigator, can come from a university, and you write a proposal to NASA that says, "Dear NASA, I have the world's coolest idea, and I think you should give me $20 million. And I have done all sorts of work to prove to you that this idea is going to work. I have put together a whole team of people who are going to work on it with me, and we have a detailed budget of exactly how much it's going to cost. It has to launch, it has to get prepared, get ready, launch, do its entire mission in 5 years or less, and it has to do it for less than $20 million. And so this has a team of people from across the country working at a variety of different, national labs, universities, companies to put together the proposal like this. And it also is a sort of mission that's going to involve a lot of student support. So these are some of the students at George Mason University who have been already kind of folded into the mission, helping on various aspects. What are we going to observe? How are we going to observe it? Well, how do you calculate things? Now, I don't know if you've ever been at a talk with a NASA mission before, but everyone at NASA seems to start their talk with an organizational chart. I don't really understand why. But what that does is it gives you a sense of just how many different aspects are folded into a mission like this. So at the top, you have the people who are principal investigators, lead investigators, science team leads, project managers. Then, because we have to actually build a physical satellite, there's a whole team of people who are systems engineers who are working on the electronics or the lasers or the payload itself. And then there's a whole other team of people who is working on the science aspects of this. How good do things need to be? What are we going to look at? How are we going to measure it? And so I'm involved in that science team side. Okay, so what actually is Landolt? This is a Pioneers class mission, one of the newest ones. We proposed this in 2023 and got selected in 2024. So we have 5 years from October 1st, 2024 to do the entire mission. And what we're doing is we're putting a box of lasers into space, and then we're going to stare up at them from the ground with telescopes. And the reason we want to do that is because we want to calibrate exactly how bright in absolute numbers the stars are. Because like I was saying originally, almost everything in astronomy requires knowing how bright things are. And so if you mess up how bright things are, you predict that you have giant galaxies at the beginning of the universe that could never have formed, or you have, impossible planets. And so, it's very easy if you just kind of shift everything down a little bit to make these very exciting headlines go away. And the reason for this is kind of this relationship between accuracy and precision, right? If you're thinking about hitting a target, you want to hit the center accurately and precisely. If you're not precise, you will average on hitting the center, but not hit it very often. If you are precise but not accurate, you will hit somewhere that is not the center very often. And then you can have, a mission that's not accurate or precise, and that's not very useful to anybody. And astronomers are very good at measuring kind of the precision of how bright things are, but they're not so great at the absolute numbers and the accuracy. So, hundreds of years, for thousands of years, people have stared up at the sky. And you can tell just by eye, this star is brighter than this star. And you can catalog them into bins. This is a star of the first magnitude. This is a star of the second magnitude. This is a star of the third magnitude. And your uncertainty on that is tens of percent, 50%, maybe 100%. And you just kind of stare, but we've been doing that forever. You can look at maps of the sky from hundreds of years ago. And then we had a jump in technology where we had these emulsion photographic plates. It was kind of like photographic film in a giant glass plate form. And in those plates, you could get the measurement of how bright the stars were to about 10-ish%. And that lasted until, there are actually these big giant plates. You used to have to put them on the back of the telescope in the dark, make sure you put them on the right way and turn on the vacuum pump and all of that. And then, they just developed this new technology called folder multiplier tubes, which allowed you to make measurements of how bright things were much more accurately. And both the increase in the accuracy of those measurements, as well as the relative precision, which one was brighter than the other. And then we got CCDs, which is kind of like the camera in your cell phone, which allows you to take a picture. And those are good in absolute numbers to about, 0.5%, 1%, something like that. But they allow you to do very good relative photometry. Is this star brighter than this star? To 0.1% from the ground. Now you can do, we've been improving the technology of digital cameras for decades, and they're getting better and better. And we're getting very good at how bright things are relative to each other. And if you launch the whole camera into space, now you don't have to worry about the atmosphere, you don't have to worry about the dust, you have a lot of things you don't have to worry about. And so you can get that relative precision to tens of parts per million. And that's actually what I use for my kind of other pieces of my science, to look at how the stars vary at that level over time to understand their internal variability and their pulsations. But you'll notice there's still this gap of, we know how it's varying up and down relative to stuff, but the actual absolute accuracy of how bright the stars are has not gotten better at the same rate. And that's the knowledge gap that Landolt is designed to fix, because we want to have an absolute metric for how bright these stars are. Okay, so you have your telescope, you have your camera, you got the light coming in through the atmosphere, it's reflected on however in the telescope and put on your camera itself. And inside that camera, you have some sort of detector, which has its own internal electronics. It has various different methods to like count the individual number of electrons that have been liberated in that particular pixel over the time of your image. When I teach this to my class, they are surprised to learn that those cameras are not perfect. And every so often, an electron will just float off. Or, you know, you'll have the sky itself is not perfectly dark, especially if you are observing from campus in Gainesville. And so the whole CCD will be lit up a little bit. And so you can correct for some of those things. And we work through how to do that in class. But it means you're kind of stacking all of these different uncertainties and different uncertainties on top of each other, trying to basically say, how much light am I getting around this particular star relative to what is happening in the pixels around it? To measure how many counts am I getting in my instrument for this particular star. And that number will be given to you in number of counts, which is not exactly the right unit for understanding how much light the star is putting out, because that is modulated by how did your particular camera convert the photons that it saw into electrons that it could count. And so when we are actually trying to measure the brightness of stars, we have to calibrate that to some system. And the kind of original system, the system that we have, is we have 4 stars that we know very well. One of them is Vega, which you can see with your eye. And when they sent up sounding rockets pretty early on, they were like, great, how many photons am I getting above the atmosphere of Earth? I don't want to deal with the atmosphere. I don't want to deal with anything complicated. I want to know how many photons am I getting from Vega? And then we picked these stars because there are these type of stars called white dwarfs where they don't have a lot of complicated lines. Somebody showed a spectrum earlier where you could break the star's light up into its different wavelengths, be able to see the different lines from all of the different elements in that star. That is very complicated. How are you going to average out over those? We don't want to deal with that at all. So they picked for these kind of standard stars, these white dwarf stars that have hydrogen-dominated atmospheres, and really the only lines you see in their spectrum are the lines of hydrogen. So you can kind of model and work around that. And so they made these models, given what they had for the measurements of the fluxes of these particular stars, to say that is how bright things are. All of these will be relative to these stars. And then people like Arlo Landolt measured those standard stars and another star, and those standard stars to another star, and those standard stars to another star, and built up this whole set of stars across the sky where they had measurements on this scale, benchmarked to these 4 original stars. And so that means that if you're observing in the night sky and you want to do relative photometry and be able to convert that to an absolute number of how bright things are, you have to take a picture of one of these standard stars and then take a picture of a star that you care about, and kind of go back and forth until you can understand how bright things are and what your number of counts that you're getting in detector means in terms of absolute brightness. And then, unfortunately, when you are actually observing from the Earth, there is an atmosphere in the way. It is great because it keeps us alive and all of that, but it is unfortunately absorbing light as it comes from space to your eye. And so if you look at things straight up, they will appear to be brighter. If you look at them almost at the horizon, they will appear to be significantly fainter. So not only do you have to measure how many counts you're getting and convert that to a brightness, an absolute brightness that you see, you then have to do another conversion between the brightness that you see today with your particular measuring setup and the absolute number of photons that are coming out of that star. And we've put together the system. It's complicated, but you can see how it would work for a lot of different observations over a long period of time. And so you could build up a catalog using these kind of standard stars as a basis to say, okay, how bright is that one? 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 And people did a lot of work to do that, to make these giant catalogs for large numbers of stars in the sky, hundreds, thousands, millions of stars in the sky. How bright are they? And so those catalogs exist, and they allow us to do all sorts of interesting science. How bright is the star relative to this other star? Are they the same brightness or a different brightness? Is this star's brightness varying over time? What type of star is this? And this has been a system that's worked great for decades. But then somebody decided to go back and re-look at those original models for those original stars. And they regenerated them, and they decided they were off by 1%. Which is a little bit unfortunate, because you notice there was a whole giant pyramid of lies stacked on top of those models that we have to now shift over to the left a little bit. And so that means we have to kind of alter every catalog that comes from that catalog, that comes from that catalog, and every piece of science that builds upon that catalog that's built upon these stars, which is not great. And, we can do that once, we can fix it once, but we really don't want to have to fix it every 5 years for the next 100 years. We want something that's going to be some independent approach, something that's much more like the kind of, SI units that you use in a lab. The kilogram is a unit. We all know, we all agree on what the kilogram is, and we will count from there. And for a while, there was some physical kilogram kept in a vault, and you would do relative to that. So we would like to have some sort of SI traceable way of understanding how bright things are. And that is important, particularly important now, because the missions that NASA is doing, these big missions, NASA, the NSF, the big projects people are working on, things like the Vera Rubin Observatory, which you just saw the really cool photos from, the NASA Roman mission that we are hoping will launch next year. Those are doing huge swaths of the sky, or very deep swaths of the sky. They're measuring the brightness of so many different objects for so many really interesting projects that we'd rather not have to recalibrate those answers every 5 years. And we would like to have absolute numbers so we can maximize the value of each of those projects. And so it would be really great if we understood how bright things are, because almost everything in astronomy is kind of balanced on this understanding. Our thoughts about the cosmology of the universe, our thoughts about planets and their habitability, our thoughts about stellar physics and stellar evolution. So what is the Landolt mission actually going to do? So we are interested in several different science cases. That includes the cosmology distances to, how big is the universe? What is the universe made of? How is it expanding over time? All of those things require knowing how far away things are, which means you need to know how bright they are. And so we've got to calibrate it for that reason. Let's skip these a little bit. For people who are interested in habitable planets, if you want to know how big a planet is to see if it's kind of Earth-like, you usually make that measurement relative to the star that it is orbiting. So you get a measurement of the ratio between the radius of the planet and the radius of the star. If you change the radius of the star by 10%, suddenly your planet looks less like Earth and more like Mars or Neptune, which is unfortunate. And for people who want to do stellar astrophysics, we have to have this network of calibrators that we can use for cross calibration for these really large surveys. Because the flux goes into our understanding of the luminosity and the temperature, which goes into our understanding of the radius and the mass, which goes into our understanding of things like the age or the planets around it. Okay, so how are we actually going to do this? What is the architecture of this mission? The idea is that we are going to launch the box of lasers into space. It's going to take a couple of days to get, oriented and launched and deployed. There's going to be some early operations where we got to test some stuff, recalibrate some stuff, make sure we understand what's working. And then there's going to be a primary operations period where you can request that those lasers be sent down to your observatory for your particular observation. And then eventually, we do not want to leave the space junk is trash orbiting in space, so it has to move to an orbit where it can deorbit itself. So this is going to be about a 1-year mission. We're hoping to calibrate enough stars over the course of that year that we can use those stars to calibrate everything else. And we're going to do this with a network of ground stations, telescopes, both in North America and South America, where we can calibrate how bright things look in that telescope. We've got telescopes in Hawaii, telescopes in Chile, and then George Mason, which is where the PI is at, has their own telescope that we're going to use for this as well. And we're going to do this both in the optical wavelengths as well as in the infrared. So we're hoping to launch to something like a geosynchronous orbit. So geostationary is where it's always in the same place in the sky. That is a little complicated, kind of a crowded orbit, and it doesn't allow us to do both the northern and southern kind of hemisphere. So we're going to be in something we think is probably closer to geosynchronous orbit, so that we can be viewed in telescopes from like Arizona to Chile. The idea is that there is going to be a range of visibility of stars that our satellite will kind of fly by. So if you've been looking at night and you've seen one of those kind of like big constellation satellites go through, maybe a Starlink or something like that, you'll notice that the satellite is moving relative to the stars behind it, and it appears to be crossing through the sky relatively quickly. That is also going to be true of something like Landolt. So we don't have an opportunity to just park ourselves next to our favorite star and sit there forever. You will have Landolt come by your star, and you better capture it while it goes by. And so there will only be a certain range of stars that it will get close enough to be imaged in the same observation. That means that like the satellite's going to be moving relative to the stars. And so if you've set up one of those telescopes that has tracking on it that kind of follows the stars with it, this satellite is not going to track at the same rate as the sky. So we've been playing games on the back end trying to understand, do we track the stars? Do we track the satellite? Do we track halfway between the stars and the satellite so that they're in the same frame for the longest amount of time, to try and understand what the best way to observe something like this is? Because you probably, in most kind of professional CCDs, you have about 90 seconds where Landolt goes through your frame, which is not very long to get a lot of data to do this calibration. We are hoping that it will be in such an orbit where it is visible in the northern and southern hemisphere and over America, rather than over Europe or Asia or Africa. But because of our launch constraints for missions like this, which is that you don't get to get your own very special launch vehicle, you have to ride share with somebody else's telescope or satellite or mission. It means we don't know exactly what orbit we're going to be in until right about before we launch it. So we're playing around with like what range of orbits are allowed. The more orbits you allow, the less constrained you are on when you can launch, which means you can catch a ride more easily. If you're very specific about exactly what launch you have to have, then you better hope that the guy who's launching in that orbit has space for you. So we're playing around with that a little bit. And we are also thinking about like what exactly is the box of lasers that we're launching. So we want to have something where we have at least 6 lasers on it. It's probably going to be 3 in the optical and 3 in the infrared, near infrared. We've also got a couple of, previous missions that have gone up or have developed hardware for a mission like this that we can rely on. So we don't have to invent everything from scratch. There was something called OrcaSat, which was a very, very small CubeSat that got launched from the International Space Station a couple of years ago. It didn't do everything that we're hoping Landolt will do, but it gave us a little sense of how things might work. And similarly, there's something called candles where they're trying to work through some of these engineering design choices. Because there are a lot of choices you have to make, right? You have to have the lasers, and how are those lasers driven? And what frequencies are they at? How are they powering? How many lasers can you turn on at the same time? Do you need to have all 6 lasers on at once, or can you do them 1 at a 2 at a time? You have to make sure those lasers are qualified for space. You have to think about how do you make a laser bright enough that you can shoot it from orbit and still be able to see it. Now, you won't be able to see this with your naked eye. We're thinking it's going to be something like 15th magnitude when the lasers are on, but there's some trade-offs there. If we're farther away, then we need a stronger laser to reach that power. And if we're closer, you don't need the laser to be as strong, but everything's going to move more. So there's some trade-offs that we're working through. There's also a couple of tech demos that we're playing around with, trying to understand, can we get something that's not just one wavelength? Can we do a range of wavelengths? But the way we're hoping this will work is that you will characterize these lasers very carefully at the National Institute of Standards and Technology, NIST, where you say, okay, I know exactly how many watts of power is coming out of this laser. And I have carefully measured my telescope. So I know if I put in 1 photon, I get out this many photons. If I put in, exactly this much light, I get out exactly this much. So we have to calibrate all the telescopes on the ground, make sure we understand exactly how much light goes through them. And then we have to set up something on the satellite where we know exactly how far away that satellite was when you tried to observe it and how much light the laser was putting out at that moment. Because then you know how much power you started out with on the satellite, you know how far away you are, and you know how bright that Landolt appeared to be to you, which means that you now have an absolute reference to be able to say, okay, this star is this much brighter than Landolt, which I know the absolute number for. And so now you turn that relative or differential photometry into absolute photometry. Now, this is just going to be a laser pointing down from space. It will be requested by professional observations, especially those that are part of our mission. But when we are pointing that laser down, it will not only be visible from those telescope sites. It is very hard to get a laser beam confined that much. So sites nearby will have an opportunity to see the Landolt beacon as well. And so we're going to have a website where you can actually see where Landolt is pointing today. And so if people want to observe it, that would be an option. And we think we're going to use some sort of ground observing mode where you have kind of the stars streaking one direction and a satellite streaking the other direction. So those streaks have about the same amount of size, and you can compute exactly how many photons you're getting from the star and from the beacon at roughly the same quality. Now, they've been testing this with some of the satellites that are already up there. Now, they don't have laser beacons, so you're looking at reflected light, usually from the sun. But you know about how much light is supposed to be reflected. You can figure out where those satellites are supposed to be and see if you can track on the satellites, the stars, and the combination to actually measure how bright those satellites are. There's a little bit of complexity here because Landolt is a box in space. And as we mentioned, the satellites all reflect light from the sun. So if you're trying to do this absolute calibration, you don't actually want this reflected solar light if you don't have to. So there's going to be some moment where Landolt is just behind the sun and therefore doesn't, just behind the Earth relative to the sun, and therefore doesn't reflect the sunlight. And those will probably be our prime observation windows for our absolute photometry. And then we have to be a little clever about how we actually extract the number of counts we're getting on the detector. We have to be careful about how we're dealing with these streaks and stuff like that, how that's going to add to our error analysis. But as I was saying, this is a place where we can compute from beginning to end, from the uncertainties on the physical laser itself to the uncertainties on the telescope to the uncertainties on our measurements, exactly what our error budget is going to be. so that we can get our absolute flux numbers to less than 0.5%. Okay, so functionally, where are we? So we started in 2024, and we have gone through some of our kind of preliminary design stuff with NASA, but there are, there's a lot of kind of gates that NASA puts up to say, I'm not giving you the full $20 million on day one. You're going to get some amount of money, and then I'm going to check and make sure you're not doing something silly. And then you're going to give you a little more money, and then we're going to check again that this is actually going to work. And so we are going through that process, working our way towards a launch date in hopes of being able to actually do this mission in 2029. So we are, meeting regularly, both over Zoom and in person, to kind of talk about the mission, the various different components, make sure everybody's working on things in concert, make decisions about what we need to balance for the science and the engineering. Thinking about publishing some of that work, and putting together a mission that's going to allow us to do all sorts of different astronomical science at a higher level of precision and accuracy than we've ever been able to do it before. Helping us move into this kind of, precision astrophysics era, making sure that we have not swept that much under the rug. So I'm going to stop there and ask if there are any questions.
Are there atmospheric considerations? In other words, during the testing, is there going to be telescope targets that are directly beneath the satellite and then some with a slant range to see if there's any attenuation or scintillation?
Yeah, so the question was, how are we going to deal with the fact that some of the observatories are going to be directly under the satellite and some of them are going to be at an angle? And that is an issue that we are worried about. We think we can characterize the expectation difference of those two different look paths. And you should be able to get the same answer because the beacon is putting out the same amount, as long as you understand how that beacon spreads. So that's going to involve some tests in the lab on the laser, as well as making sure we understand the atmosphere as well as we can. And there will probably be observations of Landolt that are of the highest quality, and then some observations that are of middling quality that we can kind of benchmark together. Other questions? Yeah.
So when a site requests that the laser is being directed to them, how long do they get? What kind of window do they get?
Yeah, so that's something we're still working on. It will probably depend on exactly how many telescopes we have doing Landolt on any particular night, as well as what our beacon stability over the long time scales are. Because it's easy to turn on a laser and then it gets like a little brighter and a little fainter and then you kind of run out of power. So we're kind of expecting that it's probably only going to be the key Landolt observatories that can request the laser, and then other telescopes around them can use it as well. So there's a lot of telescopes on Mauna Kea, for example. So if we're pointing at Keck, Subaru can use it too if somebody's interested. But I'm kind of expecting we're going to do it in half nights or full nights, because anything smaller scale than that is going to be pretty complicated. But you have to time it correctly because of it moving. And so working out exactly how we're going to do the telescope observation is a very long conversation ongoing in an email that I'm ignoring because it is not a simple question.
I think that's a good chat saying, great speaker, thank you.
Oh, thanks.
Dana Ross.
Thanks, Dana.
What about changing characteristics of the laser over the year?
Yeah. So we are hoping to have some sort of photodiode on the satellite. Oh, how are we going to deal with the fact that the laser is going to change over the course of the year? We are hoping to have some sort of photodiode on the mission, on the spacecraft itself. That's on like a little kickoff mirror, basically. So that we can understand exactly how many photons are coming out of the laser at the time of the observations, because we do expect that it's going to vary a little bit certainly over long periods, as well as over short time scales. Yeah.
How do you point a laser to a specific spot?
Yeah, how do you actually point a laser? So it's kind of the opposite of pointing a telescope at the sky. I think it's gonna work. We're gonna use a lot of the techniques that we use to point space telescopes extremely precisely. So that's something we've been able to do very well using kind of guide stars to understand like, okay, this one shouldn't move and this one shouldn't move and this one shouldn't move and I should be pointed in the middle of those. And then, correcting that pointing stability. There's gonna be a lot of math hidden on the back end to make that work. But it should be relatively good because we are very good at pointing telescopes at a particular star in the sky. I think we're going to be able to point it at a particular spot on Earth as well. We have a little bit of give left and right because the beam's going to be many miles across. So we don't have to be perfect, but we have to be pretty good. And I think we're going to be able to do that.
Any other questions? All right.
Well, thank you so much for having me.
Don't you go anywhere now. I got something for you. Nobody gets away here without a little token of our appreciation. We have one of our cups with the club logo and her name and the date and everything. Alachua Astronomy Club. Thank you so much. Yeah, I can tell that she keeps her students' interest. She's a dynamic speaker, so you don't nod off in her class. Okay. All right, so our guest speaker next month is Dr. Jessica Lee. I'm sure you know her. Talking about UV emissions surrounding galaxies. And then our members' corner speaker will be Dr. Hennig, talking about the Alvin Clark 10-inch telescope. So you'll be hearing about a really cool. It's an 1884 10-inch telescope. It's really cool. Okay, anything else from anybody? All right, hope to see you at a start party in the next meeting. Thank you.